Hello everyone and welcome to Chemistry 152. This is technically Lecture 2 on intermolecular forces, but Lecture 1 was just the introduction lecture, just going over syllabus, policies, things like that. So this is the first lecture that is covering actual material. If you've taken me for 151 before, or if you've watched my lecture videos before on YouTube, you know that in the past, what I did with Chemistry 151 is I broke things down into chapters. So Chapter 1 lecture videos, Chapter 2, Chapter 3, and so on, all the way through the first 9 chapters. Here in General Chemistry 2, or Chemistry Chem 152 is the shorthand, I'm going to be doing things a little bit differently. I am not going to be following the chapters in exact order, so we're not going to go directly into, though ironically this is Chapter 10, we're not going to flow directly then, 10, 11, 12, and so on throughout the course of the semester. I have them divided up and rearranged in a slightly different way that doesn't exactly follow the order like I did in 151. This is just what I believe is the best way and the best order to learn the material in 152. So, with that being said, we're going to go ahead and start this off. General Chemistry 2, Chem 152. We are going to begin our first content lecture on intermolecular forces. And so this is OpenStax section 10.1 and 10.2. So let's get started. First, let's talk about the different phases of a substance. So from Gen Chem 1, you're familiar, we've got solids, we've got liquids, we've got gases. Obviously, we have things that are aqueous too, but the three main phases of compounds are solids, liquids, and gases. Now, the relationship between these three phases can be analyzed based on two key factors, and that's the strength of the intermolecular forces, which we're going to be breaking down, or we're going to be using the shorthand IMF here, so the IMF strength, versus the kinetic energy, or Ke. So now remember, kinetic energy here, in this case, just really refers to how fast the molecules are moving, how quickly they're moving around. So something, an object or a compound that has a very high temperature has a really high kinetic energy because the molecules are moving very quickly. So IMFs, these intermolecular forces that we're going to learn about here, they hold molecules together. So the prefix inter, we're going to discuss what that means in just a minute here. But IMFs, these hold molecules together, whereas the kinetic energy, so the movement and energy of molecules, breaks them apart. And so it's the relationship between the two, right? If we increase the kinetic energy of an object, basically we increase its temperature, we know intuitively that objects tend to go from solids to liquids and then to gases. The reverse relationship is true if we increase the intermolecular force, or the IMF strength. And so we'll see that in a little more detail in the coming slides. So first, let's do a quick review on molecular polarity and the properties of water. So water here is a basic diagram of what the geometry of water looks like. So if you recall, again from Gen Chem 1, this has a bent geometry, which is why I'm showing it with this geometry in this form right here. Our two hydrogen atoms are oxygen atoms. These two hydrogen atoms, the bond angle between them is around 104.5 degrees because we've got two lone pairs on the oxygen atom up here that are pushing this bond, or these two bonds, closer together. And so we get this dipole moment that occurs where we have this partial negative charge represented by that Greek letter delta on the oxygen atom, and these two partial positive charges on the hydrogen atoms, right? We've got that bent molecular geometry, those partial charges, because these bonds are polar. These bonds are polar because of the difference in electronegativity between oxygen, a very electronegative atom, and hydrogen, a weakly electronegative atom. Now, these partial charges can result in a certain type of intermolecular force that is going to be between water molecules, and this can lead to some pretty interesting properties of water. All right, so just like a bond is a force within a molecule, we can also think about intermolecular forces. These are forces between separate molecules. So the prefix inter means between, whereas the prefix intra means within. So if you think, if you have heard of, intramural sports before, intramural sports means within. So that's when students from the same college play each other in, sports for fun. Whereas intermolecular, or inter, means between. So this would be, if two colleges played each other, that would be an inter relationship. It's a force here that is between separate molecules. So we're looking at the forces that hold these separate water molecules together. We're going to focus on three types of intermolecular forces, or IMFs. We're going to learn about hydrogen bonding, dipole-dipole interactions, and dispersion forces. So just to review this one more time, bonds, again, are intramolecular, meaning they are within molecules. These are strong forces that are between atoms in a molecule or ions in a crystal lattice. So, ionic compounds, ionic bonds, these are also considered to be intramolecular. They're within molecules. So the two main forces we're talking about here are two main types of bonds. Just to review, are the ionic bonds and, of course, covalent bonds. If you are going to break bonds, this would be taking a molecule and breaking it apart into its individual atoms. So breaking bonds breaks a molecule into individual atoms, and bonds are very strong and require a lot of energy to break. So water, for example, to break these two bonds would require 930 kilojoules of energy, provided if we had a mole of those molecules. Intermolecular forces, again, inter meaning between. So these are weak forces that are between separate individual atoms or molecules. Again, the three types we're going to look at are hydrogen bonding, dipole-dipole interactions, and dispersion forces. So right here, this is an example of hydrogen bonding. These two water molecules interact via hydrogen bonding. So this right here is a hydrogen bond. This is a bond between two water molecules that holds these water molecules together and keeps them in the liquid phase. To break a hydrogen bond, you are breaking a bond that's holding two molecules together, not breaking bonds that hold atoms together. So these are much weaker, require a lot less energy. So for example, to break apart 1 mole of water molecules, it would require about 41 kilojoules of energy. So a little over 20 times less energy to separate these hydrogen bonds versus actually breaking the covalent bonds that hold the hydrogen and oxygen atoms together. All right, a key component to intermolecular forces, to IMFs, is molecular polarity. So you should have a strong grasp on your ability to write Lewis structures and your ability to understand the separate theory to predict the polarity of molecules. Now, as you learned in Gen Chem 1, I'm going to be referencing Gen Chem 1 a lot in this unit, polar molecules have an overall dipole moment. So think about that word dipole, di meaning two poles. You have a region of partial negative charge and a region of partial positive charge. So they have permanent regions of partial positive and partial negative charges. These charges can then attract the opposite charges on nearby molecules. So the partial negative charge that forms on this atom in this molecule will be attracted to the partial positive region on the opposite end of the one of those same molecules. Now, nonpolar molecules, something a little weird happens with them. They have these things called transient or temporary dipoles. So this can briefly induce weak dipoles in nearby molecules, and we will learn and I will explain this in further detail later on in this video when we discuss dispersion forces. For now, let's focus on this idea of polarity, these regions of permanent partial negative and partial positive charges and how they lead to some strong intermolecular forces. We're going to start with the strongest, hydrogen bonding. A hydrogen bond is the strongest type of intermolecular force. Now, it is not stronger than a covalent or ionic bond. As we saw a couple slides ago there, it's actually still quite a lot weaker than a covalent bond. But it is the strongest type of intermolecular force. So this would be an example of hydrogen bonding. These are all water molecules. So this is what's called the space-filling model of atoms. So the red spherical shapes there are the oxygen atoms, and the white spheres are the hydrogen atoms. So these are all water molecules, and this is an example of how hydrogen bonding works. We've got that partial negative charge on the oxygen atom of one water molecule is attracted to the partial positive charge on a hydrogen on a separate water molecule and that chain just continues. And we could show branching, this hydrogen could be attracted to another oxygen. We could show basically a giant chain or a giant network of these oxygens and hydrogens being attracted to one another because of these permanent partial negative and partial positive charges. Now, it's important to note here that hydrogen bonding and the next type of force we're going to see, dipole-dipole interactions, are very similar to one another. They both have these partial positive and partial negative charges on them. But the key here with hydrogen bonding, for hydrogen bonding to be present within a substance, there must be a hydrogen directly bonded to a nitrogen, an oxygen, or a fluorine atom. It has to be one of those three. The hydrogen has to be directly bonded to a nitrogen, oxygen, or a fluorine. So basically the three most electronegative atoms in the top right corner of the periodic table up there, numbers 7, 8, and 9. Hydrogen must be directly bonded. And that key phrase there, directly bonded. It's not enough for there just to be a nitrogen, oxygen, or fluorine somewhere else in the molecule. Right? If you have some sort of molecule where you have, 2 or 3 carbon atoms, and you've got hydrogens attached to the carbon, and maybe you've got an oxygen, double bonded to a carbon, but that oxygen doesn't have a hydrogen on it, no hydrogen bonding possible. The hydrogen has to be directly bonded to one of those 3 atoms, and these 3 only. So when a hydrogen atom is in a covalent bond with a highly electronegative atom, that single electron from the hydrogen, right, since hydrogen is bringing a single valence electron to the bond, it is highly attracted to that more electronegative atom. Without its single electron around it, the hydrogen nucleus has a pretty strong partial positive charge. We can say the nucleus is de-shielded. So again, drawing you back to Chemistry 151, this is all the way actually back in chapter 4 when you learned about ionization energy, when you learned about electron affinity and atomic radius size. If you remember that unit, you may have heard the phrase, or you should remember the phrase shielding. So when we refer to those different layers of valence electrons, we can say the outer valence electrons or the outer electrons are shielded from the positive charge in the nucleus by the inner or the core electrons. Similar idea here, since hydrogen's one electron is being pulled away from it, right? So basically the electrons in this bond are being pulled strongly towards that highly electronegative atom. This proton here in the nucleus basically is sort of completely exposed, right? It doesn't have much electron density around it, as indicated by the blue shading here in the electron mapping. So we can say then that this nucleus is de-shielded. So the partial positive charge on the hydrogen atom of one molecule is then attracted to the partial negative charge on another. So opposites again attract. So water again is a very good example of hydrogen bonding. So just breaking down that space filling model in a little more detail, actually showing you the atoms and their identities, and see how we can begin to have this interaction where this oxygen is attracted to this hydrogen is attracted to this oxygen, which is also attracted to this oxygen. So you can see how a network can quickly begin to form. And this is what attracts these water molecules to one another and what gives water fairly strong intermolecular forces. H bonding, however, doesn't need to happen between 2 molecules of the same compound. It is possible for them to happen between 2 different molecules, as long as one molecule has a hydrogen with a positive charge bonded directly to an NO or F, and the other molecule has some atom with a partial negative charge, or even just a lone electron pair. Hydrogen bonding still can occur. So a good example of this would be the C double bond O, so the carbon to oxygen double bond in methanol. This is methanol right here. This is the official IUPAC name, but the common name for this is formaldehyde. This has a polar bond with a partial positive charge on the carbon and a partial negative charge on the formaldehyde. This gives the oxygen that partial negative charge it needs to bond with the partial positive charge on the hydrogen atom from a water molecule. So this is still technically a hydrogen bond. So the key takeaway here is this is a major reason why polar molecules tend to be soluble in water. This is a polar molecule, and it's soluble in water because it can interact with the partial positive and negative charges on water. Now, oftentimes on homework questions, on exam questions, you may be just given an individual molecule and you'll be asked, does this molecule exhibit hydrogen bonding? And so what's being asked there is if this molecule interacts with itself, does it interact hydrogen bonding? So the answer for water would be yes, water exhibits hydrogen bonding. Whereas if you were just given formaldehyde by itself, this methanol, and you were asked, does this compound exhibit hydrogen bonding? The answer would be no. This molecule will not exhibit hydrogen bonding when it's just by itself. If you put it in contact with water, then yes, we will see hydrogen bonding. But this molecule on its own, no, will not experience hydrogen bonding because we don't have a hydrogen directly bonded to one of those three atoms. Now, hydrogen bonding is important not just for intermolecular force strength, but if you are someone who's interested in biology, you're taking biology or planning on advancing in that field, you will definitely see some hydrogen bonding. Primary area you're going to see this is when you analyze DNA. So many of the main DNA base pairs, they will exhibit hydrogen bonding. So for example, what links adenine and thymine, two of the major nucleotide bases here, they experience hydrogen bonding. This is what kind of keeps their bridge together here. A hydrogen attached to a nitrogen bonds, hydrogen bonds to an oxygen. Here, a hydrogen also attached to a nitrogen, hydrogen bonds to this nitrogen. So two hydrogen bonds that help link these base pairs together. All right, now moving on. If that formaldehyde compound I was just showing, if it doesn't experience hydrogen bonding, but it still is a polar molecule, what type of intermolecular forces does it undergo? And here we bring us to our answer, dipole-dipole interactions. So polar molecules that don't have a hydrogen atom directly bonded to NO or F still have areas of partial positive and partial negative charges which will attract each other. These attractive forces are called dipole-dipole interactions. So that formaldehyde compound we were looking at is an example. Or here, how about hydrogen chloride? So a hydrogen bonded to a chlorine. This is definitely a polar molecule with a strong partial positive charge on the hydrogen and a partial negative charge on the chlorine. Now, chlorine is not one of those three, the NO or F, so this will not form or exhibit hydrogen bonding, but it will exhibit dipole-dipole interactions. So because we've got those permanent regions of partial positive and negative charges, we can have interaction in between molecules. So the negative region here or the negative charge on this chlorine atom is attracted to the partial positive region on the hydrogen of another molecule, and that chain just continues down the line here. All right, dipole again meaning two poles. So to have a net dipole and to exhibit dipole-dipole interactions, a molecule must be overall polar. So this is why it's very important you understand how to correctly draw a Lewis structure and then to interpret there from reciprocal theory and just your general knowledge on electronegativity, whether or not these bonds are polar, and importantly, what the molecular geometry of the molecule is. So here, this molecule, this is CH3Cl. So this is going to have a tetrahedral geometry, which is generally symmetric, but only one of the terminal atoms is a chlorine. So this molecule is going to be polar. These three bonds, the carbon to hydrogen bonds, are nonpolar, but the carbon to chlorine bond definitely polar because of a large electronegativity difference between these two atoms. So we get a partial positive charge on the carbon, a partial negative charge in the chlorine. So what we would see here is then that partial negative on the chlorine would be attracted to the partial positive charge on the carbon on another molecule. So this is that dipole-dipole interaction. Dipole-dipole interactions, again, you can see are very similar to hydrogen bonding, but the key difference, we don't need a hydrogen directly bonded to NO or F. Any polar bond works. And now it's important to note that dipole-dipole interactions are weaker than hydrogen bonds, since we're not going to have as strong of partial positive and negative charges as we saw with hydrogen bonding. Now, to have a dipole, the distribution of electron density must be uneven across the molecule. So again, this is kind of referring to what you learned about in Chem 151, but we're adding a little more detail here. So the first and most obvious case is if you have a polar covalent bond with asymmetric molecular geometry. Definitely a polar molecule, definitely going to experience dipole-dipole interactions. So that would refer to the first example, carbon monoxide. We've got a polar covalent bond between the carbon and the oxygen. And, oh, actually, I'm sorry, this does not line up with what this bullet point here, my mistake. But this is a polar molecule. I'll get to it in a second. Polar covalent molecule, asymmetric molecular geometry. So this would be like water, actually. This would be a better example. Sorry for that poor example there. Better example would be water. Water is a polar covalent bond. It's asymmetric. It's got an asymmetric molecular geometry. Or maybe something like H2S. So two hydrogen atoms with a sulfur atom in the center. It's still going to have that bent geometry like the water molecule does, but now we've got sulfur in center instead. So that's going to be dipole-dipole interactions. If you've got a lone pair of electrons, that leads to an asymmetric molecular geometry. So again, this would be bent or something like trigonal pyramidal, right? Think about your asymmetric or your unbalanced molecular geometries when you learned a separate theory in Gen Chem 1. Now, if we've got an unbalanced formal charge, so unbalanced formal charges will often lead to dipole-dipole interactions. So this indicates that electrons are being overshared or undershared, which is going to slightly affect the electron density, and ultimately it's going to affect the geometry. So the three main takeaways, all three of these bullet points really point towards the direction of look for an asymmetric molecular geometry. If you've got an asymmetric molecular geometry, polar bonds, lone pairs of electrons, unbalanced formal charges, all of these things lead towards a molecule being polar, towards having a dipole, which means it's going to have dipole interactions. The few slightly more tricky examples, these two you definitely saw in Chem 151, so now more appropriately discussing this carbon monoxide example. This carbon monoxide molecule here, it is symmetric, right? It's got a linear geometry. We do have lone pairs. Both the carbon and the oxygen actually do have a lone pair in this geometry. It's symmetric because of its linear geometry, but it does have a polar covalent bond here. This triple bond is polar in the direction of oxygen, so partial negative charge on oxygen, partial positive charge on carbon. This molecule has two unbalanced regions of a permanent negative, partial negative, and partial positive charge. This molecule does have a dipole. It's a polar molecule. It would experience dipole-dipole interactions. CO2, carbon dioxide, you might again remember this example from 151. We do have two polar covalent bonds here, but because the geometry is symmetric, these two polar covalent bonds cancel one another out. And so this molecule actually does not have a dipole and would not experience dipole-dipole interactions. It's a non-polar molecule. Now the last example, and the one that's a little weird, is ozone. Ozone, you would think this molecule would be nonpolar because it's three of the same atoms, three oxygen atoms, but it is in fact a polar molecule. It does have a dipole. The reason for this is it hits on two of these, well actually really it hits on all three of these. We've got an asymmetric molecular geometry, so we've got a lone pair on the oxygen, right there. We've got a lone pair of electrons on this oxygen. Both of these oxygen atoms have lone pairs. We've got a bent geometry because of the lone pair on the central atom, and we are going to have an unbalanced formal charge. If you break down what the initial Lewis structure looks like for ozone, it shows you an unbalanced formal charge. We get these kind of weird like half bonds when we touched on resonance forms. So ozone, because of its asymmetry, it does actually have a small dipole, and so it is considered to be a polar molecule that would have dipole-dipole interactions. All right, these dipole-dipole interactions can be quantified with something called a dipole moment, or we usually use the capital letter D. So if we look at a few different examples, first let's start with propane. Propane, CH3, CH2, CH3. So this molecule is non-polar. So if you go ahead and draw out the Lewis structure of this, you'll see that it's just composed of a 3-carbon chain with hydrogens single bonded to all the carbons. Carbon and hydrogen have roughly the same electronegativity, so their bonds are nonpolar. and the geometry is going to be completely symmetric. So this molecule is completely nonpolar. So we can see basically a dipole moment of 0. So it's a nonpolar molecule. We can also see we've got a pretty low boiling point. And we're going to see in a little bit the relationship between IMF strength and boiling point. These next couple molecules, you'll notice, all have non-zero dipole moments, meaning they are all polar. And I would welcome you to pause the video and take a minute just for some good practice. Draw out the Lewis structures of these molecules and see if you can figure out or analyze why they are polar. All right, I've also got 2 more practice problems for you here. So go ahead, I recommend pausing the video and giving these a try. First, explain the difference in boiling points between acetone and 1-propanol. So this is acetone, this is 1-propanol. Second, the molecular mass of butanol is given, and its boiling point is given. This is butanol on the left. The molecular mass of ethylene glycol and its structure is given on the right with its boiling point. Also answer the question, why do these 2 things have such different boiling points? Okay. Oh, sorry about that. I thought I had the answers on the next slide. Briefly, if you hopefully you had a second to pause the video and give these a try. But as we're going to see later, I can't remember. I think it's later in this lecture, if not in the next unit. The big thing to hammer on here, and you may have picked up on this trend in the previous slide, there is a direct relationship between intermolecular force strength and the boiling point of a substance. So we can see the non-polar molecule has a very low boiling point, whereas the molecule that is much more polar has a much higher boiling point. If something is more polar, it's got strong dipole-dipole interactions, it's harder to pull the molecules apart, so it takes more energy, thus a higher boiling point. So here, we can see this molecule on the left, acetone, you should have identified that it would experience dipole-dipole interactions, whereas this molecule on the right, 1-propanol, would experience hydrogen bonding, or it would exhibit hydrogen bonding. So hydrogen bonding is stronger than dipole-dipole interactions, meaning that 1-propanol is going to have the higher boiling point. We can say something similar down here. They're both going to exhibit hydrogen bonding, but the one on the right will have, well, quite simply, more hydrogen bonding because there are 2 OH groups instead of just 1. More hydrogen bonding, stronger intermolecular forces, takes more energy to pull the molecules apart, and thus a higher boiling point. All right, now let's talk about dispersion forces. So generally, the distribution of electron density around a non-polar molecule or atom is symmetric and uniform. These things are typically gases at room temperature. So these molecules right here, it's some sort of non-polar molecule where these 2 spheres right here represent the nuclei, and then shaded purple there, that represents the electron density. So if you think back to the electron heat maps we saw earlier in this unit, where we had those polar molecules where the less electronegative atom had that like blue shading, and then the more electronegative atom had the red shading. Red meaning a lot of electrons, blue, no electrons. So purple then obviously is in between. So we have a nice even distribution of electrons all across the entire molecule, meaning it's non-polar. However, even non-polar gases such as nitrogen gas, N2, and argon are known to have some type of condensed, either liquid or solid phase. So there must be some sort of attractive intermolecular force that can bring them together. So dispersion forces are these attractive forces. What's going on here? Well, when the electron density around a non-polar molecule randomly becomes non-uniform, the molecule gains what is called an instantaneous dipole that is temporary in nature. This dipole can then spread to nearby molecules, giving them an induced dipole. The resulting attractions are called London dispersion forces, or we're going to simply call them dispersion forces. So one molecule, we get a random instantaneous dipole, and then the nearby molecules respond to that random instantaneous dipole and begin to form what is called an induced dipole. So their dipole is induced by the dipole in a nearby molecule. Now you're probably asking, why is this happening? How does a dipole how do we even get this initial random instantaneous dipole? Okay, well, let's break this down. Dispersion forces, they result from a momentary shift in electrons in a non-polar molecule, which causes a temporary or transient dipole. Again, this transient dipole is going to influence the nearby molecules. How does this happen? All right, so we're starting with this image right here. So suppose we've got hydrogen gas, those two hydrogen atoms. So we've got that covalent bond, and those two electrons are being evenly distributed across the entire molecule. Their density is evenly distributed across the entire molecule. Now I want you to think of these two electrons and this purple shading here, kind of like it's like a cloud of electrons. And so these electrons, they are always, moving. They're in constant motion. They are not just static, just sitting right on an atom. They are in constant motion, just circling randomly. Those two electrons constantly moving and circling all across the molecule. Now, what can occur is just purely by random, purely by chance, by happenstance, it is possible that both electrons find themselves on one side of the molecule, with meaning we have no electrons on the other side of the molecule. So just as part of their random motion, two or both electrons, or in the case of a more complicated molecule, a large mass of electrons find themselves on one side of the molecule, and we have a lack of electrons on the other side of the molecule. So what happens then is we get that temporary or transient dipole, where just for a moment we've got too much electron density on one side. So we get that partial negative charge as indicated by that little Greek letter delta there, a partial negative charge on one side of the molecule and a partial positive charge on the other side of the molecule. So this is what happens. Now it's important to note here in my diagram, these actually represent two different molecules, and we're going to see how this molecule affects this one. I was just treating this like this was the before and after of one molecule for the purposes of the explanation. Ultimately, the point is we get that random momentary shift of electrons, which causes a temporary dipole. And then what happens? The adjacent molecule, so again, this is our first molecule where that temporary dipole forms, and the adjacent molecule is going to respond. So now we have a partial negative charge on this side, so the electrons in this molecule are going to be repelled, right? Those similar charges repel each other, like when you try to put two ends of the same magnet together, they repel one another. So the negative charge on this side of the molecule repels the electrons in this molecule, and so now we get a dipole forming in this molecule as well. So we've got that original dipole. Now this other molecule has that temporary induced dipole. And so now we've got the charges we need. We've got this temporary partial negative charge and this temporary partial positive charge. This attracts these two molecules to one another. And so this is how dispersion forces function. And we could continue this chain, right? We could look at the molecule on this side, where we'd have an induced dipole with a negative charge on the right side of the molecule. We could also see it happening down the line. It could happen over here now. This molecule had an induced dipole, and then suppose there was another molecule right here. This induced dipole could induce a dipole in this molecule with a partial positive charge here and a partial negative charge here, and the chain could keep going, and this is what causes the formation of these dispersion forces. It's important to note that dispersion forces are the weakest intermolecular force due to their temporary and small nature. Now, everything technically has dispersion forces. All molecules, all atoms, all ions, they all have dispersion forces because their electrons are all capable of this movement. Now, for polar molecules and for ions, we generally don't consider dispersion forces when we're analyzing intermolecular force strength, since dipole-dipole interactions and hydrogen bonding are much stronger than dispersion forces are. But again, it is still important to note that everything has dispersion forces. So if you encounter a question where it gives you a polar molecule, let's say it gives you the molecule water, and it asks you what type of forces did this molecule exhibit, you should select dispersion forces because it still does experience dispersion forces, but of course we just care more about the hydrogen bonding in that example. Now, how can we analyze the difference in dispersion force strength? Because now, not all dispersion forces are created equal. And one thing that's important to note here is the size matters a lot. The size of the molecule, the atom, whatever it is going to significantly affect the strength of those dispersion forces. So there's a key term to note here, and that is polarizability. Polarizability is how easily the electrons around an atom or molecule can be shifted to one side or another. Polarizability depends on atomic size and electronegativity. So electrons that are further from the nucleus are held less strongly, and electrons that are on less electronegative atoms are also held less strongly. So electrons that are less strongly held are considered to be more polarizable, which means the dispersion forces are stronger. So a good example of this would be iodine atoms versus fluorine atoms. So let's say we have the molecule I2 versus the molecule, F2. The iodine atoms are much bigger than the fluorine atoms are. The iodine atoms are also less electronegative, right? So because of this, the electrons in these iodine atoms here are less strongly held. The atom is bigger and less electronegative. So the electrons in these iodine atoms surrounding their nuclei in the center are less strongly held, which means they are more polarizable. They can move from side to side, up and down, whichever direction. They can move more easily. So because they can move more easily, they will form stronger temporary dipoles, which means their dispersion forces are stronger. Now, if we look at those two fluorine atoms or this F2 molecule, these fluorine atoms are very small, and they are also very electronegative. So because of that, these electrons are pretty strongly held. They are less polarizable, meaning they have weaker dispersion forces. So because these iodine atoms are more polarizable, this is why iodine exists as a solid at room temperature, whereas fluorine is a gas at room temperature. So if you go down the halogens, if you look at like an interactive periodic table, like if you go to ptable.com, if you look at the halogens going down from fluorine to chlorine to bromine to iodine, as you go down the halogens there, those atoms are getting bigger and less electronegative, meaning they're getting more polarizable, and their dispersion forces are getting stronger. That's why you see a phase change as you go down the halogen list. Fluorine gas, or F2 and Cl2, fluorine and chlorine, those diatomics, are gases at room temperature, whereas bromine, Br2, is actually a liquid at room temperature, and then iodine, I2, is a solid at room temperature because as those dispersion forces are getting stronger, the intermolecular forces are getting stronger, and so you're more likely to be a liquid or a solid at room temperature. If you think back to the very first slide today when we analyzed how intermolecular force strength affects the phase of a molecule. The stronger your IMFs are, the more likely you are to exist in the liquid or the solid phase, what are referred to as condensed phases. Okay, so this is kind of just reviewing what I just talked about. But again, as polarizability increases, so either due to size and electronegativity, the dispersion force strength increases. So polarizability is strongly correlated with the molar mass of the substance. So again, analyzing that F2Cl2Br2I2, molar mass is increasing, polarizability is going up because of size and electronegativity. The state at room temperature is changing, and we can also see the drastic difference in the boiling point of these four molecules. Okay, go ahead and try and answer this question. Would H2 have a higher or lower boiling point than F2? Okay, so I would encourage you to look that one up. I think you should probably have an idea of what the correct answer is. Now we're going to move next to molecular shape and dispersion forces. So the molecular shape can also affect dispersion force strength. Molecules that have a large surface area, these molecules are going to have stronger dispersion forces and thus stronger IMFs. This is mainly due to more contact area or more interactions between molecules. This also has a lot to do with the polarizability of the substance. So if we look at the three C5H12 isomers, so if you recall from Gen Chem 1, Isomer refers to types of compounds that have the same molecular formula, but they have different connectivity. So these are what are referred to as structural isomers. Their atoms are actually connected in a different order. So these are three isomers of pentane. We have neopentane, isopentane, and then just regular pentane, or sometimes this is called N-pentane when it's in this long chain form. So these things have the exact same molar masses. They are formed of the exact same atoms. They are all non-polar, right? They're going to have the same, the atoms at least have the same level of polarizability, right? Same size and electronegativities, but their boiling points are different. Neopentane, 9 degrees Celsius, isopentane, 27 degrees Celsius, and then just regular pentane or N-pentane, 36 degrees Celsius. Why is this? Well, this has a lot to do with the shape. N-pentane is extremely branched. See how we have that carbon atom in the center there that doesn't have any hydrogen on it, and then it's branched off in 4 directions, and we have these 4 CH3 groups at the terminus here. This is a very branched and a much more spherical-like compound, and so because of this, it actually has a lot less surface area, and the electrons are they have a much lower polarizability. Whereas as we go from left to right, from isopentane and then to pentane or N-pentane, see when we have this long chain, we've got a lot more surface area, we've got more contact area, meaning we've got stronger intermolecular forces. And these electrons are also generally much more polarizable than the ones in a more branched compound are. So this is something to keep note of, to pay attention to this. If you are given an example like this where you've got atoms that seem like they have similar, they have maybe the exact same molecular formula or very similar molecular formulas, when it seems like their dispersion forces, or when they both only have dispersion forces, and you're asked, well, which one is stronger? This is a factor you may have to consider. You may need to consider molecular shape here. Something that is branched or more spherical is going to have a low surface area, whereas something with a long chain with a higher surface area is going to be stronger. All right, using your understanding of dispersion forces, please discuss why isooctane has a lower boiling point than just regular octane, or again, what we call N-octane. So I would just like you to pause the video and just think about this one, maybe write down an answer if just write down a couple lines and see if you understand the key difference here, why this compound has a lower boiling point than this compound does. All right, a little more dispersion discussion I would like you to take a look at. First, why is Ci4 a solid at room temperature with its melting point at 171 degrees Celsius, whereas CH4 is a gas at room temperature? And then I would also like you to analyze what trend explains the increase in melting point going down the column. Okay, so briefly, the answers to both of these kind of deal with the same thing. So these compounds, these 5 compounds, all have they all have the same molecular geometry. They're all tetrahedral. So we actually can't analyze this one in terms of, being more branched or less branched. This would be purely an analysis of both polarizability and molar mass. So both 1 and 2 here would have to do with the size of the atom, the electronegativity, polarizability, and also importantly, molar mass. There's generally a pretty direct relationship between molar mass and dispersion force strength. Okay, so recapping, dispersion forces, these are the weakest, but all molecules have them. For polar molecules, hydrogen bonding and or dipole-dipole interactions are stronger and thus are more important for predicting chemical behavior. So if you are asked about a polar molecule, yes, that polar molecule still has dispersion forces, but those dispersion forces aren't that important for predicting the chemical behavior of that compound. Nonpolar molecules can't have dipole-dipole interactions or hydrogen bonding, so dispersion forces are the strongest IMF possible for nonpolar molecules. When you go to compare two molecules where the strongest IMF is the same, the molecule that has the highest molar mass is likely to win. And again, dispersion weakest, dipole in between, though quite a bit stronger than dispersion forces, and hydrogen bonding are the strongest. And hydrogen bonding, remember, we have to have an H bond directly to NO or F there. Now we're going to look briefly at IMFs in functional groups. So we're going to consider the structure and bonding of functional groups. And if you're unfamiliar with this term, functional groups generally refers to a class of compounds. You will typically see these in organic chemistry. So like alkanes refers to a class of compounds that are composed of just carbon and hydrogens with single bonds between them, whereas alkenes, carbons, hydrogens, double bonds between them. Things like alcohols all have OHs, amines all have nitrogens bonded usually to hydrogens or R groups. I'll explain what those are in a minute. Carboxylic acids, amides, and we see aldehydes, esters, ketones, and ethers. The R here, R is not actually an element. There is no element R. R just refers to what is called an R group. So R groups are just some sort of other functional group, maybe just carbons, hydrogens, whatever, attached to the functional group of note. So the R groups here don't really matter for our purposes. We are just more paying attention to what's going on with the functional groups themselves. So these top four right here have dispersion forces only. Right, notice how they are composed of carbons and typically just hydrogens. They contain only nonpolar bonds. They're going to generally have symmetric geometries. So these compounds, dispersion force only. These four in the middle will have hydrogen bonding. So we have hydrogen bonded to an oxygen, hydrogen to an oxygen, hydrogen to a nitrogen, hydrogen to a nitrogen. They all contain an H bonded directly to an N or an O. These two right here that have little star, 1 or 2 degree only. This is something that's related to organic chemistry. I'm not going to touch on that here, but you'll learn about what that means in organic. Not necessary for you to know this in Gen Chem 2. And these green ones at the bottom here, these would have dipole-dipole interactions. These are all going to be polar. You can see here we've got this C double bond O, or we've got this bent geometry in terms of the ether. All going to be polar, but we don't have hydrogens directly bonded to an N or F, so we can't have hydrogen bonding. All right, this table below lists various different types of bonds you're likely to see in different compounds, whether each bond is polar, and it lists the strongest IMF it generates. So a nice summary slide here. Now I would like you to try a couple practice problems. So practice, name that IMF. Go ahead and pause the video and answer this question. What is the strongest IMF between molecules in each of the following substances? So for each of these, you are just analyzing if HBr interacted with itself. What would the strongest IMF be? Okay, and here are your answers for each of those three molecules. Let's go ahead and have you try this for these four molecules. So again, pause the video and answer for these four. Would they have dispersion, dipole, or hydrogen bonding? What would be the strongest IMF these molecules would exhibit? All right, and here are your answers for these four molecules. All right, last couple things to hit on here. Just a few other IMF categories and combinations I wanted to hit on. You may see these mentioned, ion-dipole. So ion-dipole, this is a type of intermolecular force that occurs between an ion and a polar molecule. So ion-dipole is most commonly seen when we look at the dissolution of ionic compounds. So this force is going to be very important when we learn more about solubility. So think about in Gen Chem 1 when you learn about the solubility rules, right? Maybe when you learn about how any compound that contains sodium is always soluble. Well, this is one of the main reasons why, because of these ion-dipole forces. So this would be, for example, like a positive sodium ion interacting with the negative dipole of a water molecule. Next is something called ion-induced dipole. So these names are very nice and descriptive, fortunately. So this is when an ion induces a dipole in a nonpolar molecule. That strong ionic charge induces a transient dipole in the nonpolar molecule. So for example, if we had a positive ion interact with the nonpolar molecule N2, nitrogen gas, That positive ion over here causes these electrons to shift in response. So some more electrons would migrate to this side of the molecule because they're attracted to the positive charge. This forms a temporary negative, partial negative charge or partial temporary dipole on the N2. Partial negative charge here and partial positive charge here. And the last one is the dipole-induced dipole. Again, the name is nice and descriptive. This occurs between a polar molecule and a nonpolar molecule. This is when the partial charge on the polar molecule induces a transient dipole in the non-polar molecule. So again, suppose we had a water molecule next to nitrogen gas. Perhaps these partial positive charges on the hydrogens induce a dipole in that nitrogen gas where those electrons migrate to the left to be close to those partial positive charges. So now we get that induced transient dipole in the non-polar molecule. All right. Last thing to note, as ionic charge increases, the strength of these IMFs will increase also. Last thing to mention here, I kind of just explained this on the previous slide, but ion-dipole interactions, very important. One of the best examples of this would be salt in water. Because water is a very polar molecule, it readily dissolves ionic compounds such as sodium chloride. So as I mentioned, you'll get those positive sodium ions will be attracted to the partial negative charges on the oxygens, but also there's something for the chloride too. The negative chloride ion is attracted to the partial positive charges on the hydrogens. So it is this property of water that enables it to dissolve ionic compounds. So this is why, our body can easily transport nutrients, right? This is really important for the ability of like sodium ions, potassium, calcium ions, etc., to be transported through our body. It is these ion-dipole interactions that fuels these processes. All right, here's a summary slide. This chart right here will help you break down and help you determine what the IMFs a compound will have. And then again, this is just a recap that covers the strength of IMFs. And I do want to note that this chart doesn't cover those combinations, those three combinations we saw just 2 slides ago. Okay, that is the end of this lecture. So it was titled Lecture 2, but really this was the first lecture of Gen Chem 2 on those first 2 sections of Chapter 10, Intermolecular Forces. Hope you enjoyed this lecture and found it useful. I'll see you in the next one.